Okay, John, would you like to start by introducing yourself, please?
Yes, hello, I'm John Barrow. I'm Professor of Mathematical Sciences here in the Department of Applied Maths and Theoretical Physics at Cambridge University. And I'm also Director of the Millennium Mathematics Project. And I'm a cosmologist, and I'm interested in astrophysics, gravitation physics, and all sorts of other problems in mathematical physics.
Now, physicists often pride themselves that the laws of nature are simple and elegant. But how can it be that a simple law describes the very complex world that we live in?
We have to make a pretty clear distinction between the laws of nature and the outcomes of the laws of nature. And one of the miraculous features of the laws of physics is that the outcomes of the laws do not have to possess the same symmetries and simplicities as the laws themselves. And therefore you can have a universe which is governed by a very small number of simple symmetrical laws, but whose outcomes, the solutions of the governing equations of those laws, can be almost unlimited in their complexity and diversity. So this in some sense is the secret of our universe, that the outcomes of the laws of nature do not have to possess the same symmetries as the laws themselves. A nice example is to take something simple like this pen and just balance it vertically on my hand. If I were to think about what would happen if I let go of the pen, then it becomes subject to the law of gravity. The law of gravity is perfectly symmetrical with regard to directions in the universe. It doesn't prefer that pens fall towards one particular direction in outer space. But when I let go of the pen, even if I did it at 0 degrees in a perfect vacuum in ideal conditions, it would always fall in some random direction. And in that falling, it picks out a particular direction which is not a symmetry of the underlying laws. So it's equally likely to fall in any direction. So this really is the key distinction between the laws and the outcomes. The laws are simple, based on symmetries, and the outcomes are rather complicated, and they manifest all sorts of breakings of symmetries.
And you've mentioned symmetries a lot, and in modern physics they play a hugely important role. Could you explore that further?
Yeah, if we go back about 300 years or so and before, how did physical science work? People tended to watch things in the world carefully, and they would notice that certain things always followed other things, that there were certain habits, as it were, in nature. Certain effects followed certain causes, and they gradually keep check of those, and then eventually someone like Newton might propose that there was what we call a law, that there was a rule, that if you did one thing, something else would always follow. So this was a way of predicting the future from the present. And the modern equations of physics are rather like that. You set starting conditions. You have a mathematical formula that then predicts what will happen in the future. But in the 20th century, people started to notice that laws of change usually were equivalent to a statement that something else did not change. So even in the 19th century, people like Kelvin had identified what we call conservation laws, like the conservation of energy. And there's the conservation of angular momentum and the conservation of momentum itself that Newton identified. So these are all statements that something does not change. And remarkably, these rules that if you start at a particular time you can predict the future, turn out to be equivalent to statements that something else does not change. And in the case of the ordinary laws of mechanics, the fact that the laws should be the same at every time that you use them or measure them is equivalent to the conservation of energy. And the statement that you should get the same experimental results, you should see the same laws, whatever direction you point your laboratory in the universe, is equivalent to the conservation of angular momentum. And the statement that everything should be the same wherever you observe from, different positions, is equivalent to the conservation of momentum. So these invariances, that things be the same when you make various changes, turn out to be equivalent to laws of change. In the 20th century, particle physicists took this on board to a considerable extent, so much so that they thought the symmetries and the invariances were really primary. So instead of finding laws of change that you later on worked out were equivalent to some invariance, you started by looking at the catalogue of all the invariances. And helpfully, pure mathematicians had established that catalogue long before, and it's an area of mathematics known as group theory. So it tells you the things that you can do that leave things unchanged in some way. So by looking at that collection of patterns and symmetries, you can work out which of them might be appropriate to describe certain sorts of physical interactions. And the law of the weak interaction, the strong interaction governing quarks, these are all based on rather abstract symmetries that come from that catalogue of possible symmetries.
And this approach has been very successful because particles like the famous Higgs boson and previous Z and W bosons, they were predicted on the basis of these symmetry assumptions, and then people looked for them and found them in the accelerators.
Yes. Yeah, so the way that physics developed was really, over the last 300 years, was going from more to less. So at the time of before Newton, people thought there was some force which kept the planets moving around according to Kepler's laws, and there was something else here that kept our feet firmly on the ground and made apples fall towards the earth. But Newton showed that they were one and the same force of gravity. And Maxwell showed that electricity, both static and dynamic, and magnetic forces were just different aspects of the same electromagnetic force. And so this urge to unite things, to reduce the number of forces, has been a dominant approach in 20th century physics. And what you hope is by joining, say, the weak interaction, which governs neutrinos and radioactive forces, with electromagnetism, that by joining the different shaped pieces together in the jigsaw, you might place some new constraint on the shaping of each piece, or require some new type of particle to exist that allows both pieces to talk to each other. And that was the case with electroweak unification. So these W and Z particles, 3 of them, were like heavy versions of the photon. And they mediated the unification between weak forces and electromagnetic forces. And they're predicted to be very heavy. They were predicted to be 100 times or so heavier than the proton. And they were found at CERN long ago now, and confirmed this unification into what became known as the Weinberg-Salam theory. So this is what people hope in all these steps of unifying symmetries, one with another within a bigger one, that the unification makes some new prediction that you can use to test whether this is the right step to take.
Mm-hmm. So we started with this question of how complexity can arise out of something quite simple, and there's another way in which this can happen, and that is through chaos. Can you explain that a little further?
Yeah, we talked at the beginning about you've got this separation between laws of nature, which are rather simple, symmetrical, and the outcomes of the laws of nature. And for a long, long time, the educational process at schools and universities has very much focused on the world of the laws and simple solutions, things that you can do with pencil and paper in 30 minutes under examination conditions. But I think it was in the early 1980s that there was a significant change in the approach of scientists and mathematicians. And it was brought about by the IT revolution. That suddenly there were inexpensive, small desktop computers that didn't cost very much money, that were easy to use, and they had fast interactive graphics. Before that, there were computers in science, but they cost millions of pounds, and they were controlled by huge research groups doing blockbusting problems like exploding bombs, studying supernovae, or trying to predict the economy or the weather. But all of a sudden, single individuals or small groups could study very complicated processes experimentally on the screen. So you might lay down some rules about how different types of particles interact with each other, They might be people, or they might be predator and prey and animals, and just watch what happened. And from the 1980s, early 1980s onwards, there grew up this study of chaotic and complex processes. So chaos was something that you found within many, many of these investigations. And chaos is just extreme sensitivity to ignorance. So you have a process where there's a little uncertainty in how it starts, but as you evolve to the future, that uncertainty grows dramatically, exponentially at each step. So we recognize many processes like this. The weather is like this, at least in the UK, where the reason we can't predict the weather very successfully a few days ahead is not because we don't understand the weather in some deep sense, that there is some mysterious weather force that we don't understand. It's simply that we don't know the state of the weather everywhere with sufficient accuracy to be able to predict the future infallibly. So we might measure the weather every 50 or 100 miles over the land, a bit further separated over the sea. And then you use a supercomputer to predict the future from that. But the uncertainty between the weather stations is sufficient that it grows dramatically as you run the computer, and you would end up with different weather forecasts according to how you interpolated between the weather stations. So uncertainty in the weather is a manifestation of our ignorance of the starting conditions, even though we know the laws of how the weather change very, very accurately.
So whether you find the world simple or complex depends on whether you're looking at the laws of nature or the outcomes.
Yeah, so if you're a particle physicist, gravitation physicist, you will spend a lot of time focusing on the laws of nature, how to extend them, how to express them, how to unify them. And for you, the world is preeminently actually rather simple. You're focused on the laws of nature. They are the truer reality for you. And for you, the laws have this Platonic appearance. They are simple and symmetrical. But if you're a life scientist, a biologist, an economist, or even someone working condensed matter physics or chemistry, you'll never talk about laws of nature. What biologist ever talks about the laws of physics? Because you're only interested in little bylaws and rules of thumb that happen in the complicated world of the outcomes that you spend your time trying to make sense of. You might be using game theory or studying stability, but for you the world is very complicated, and you have to use computational techniques to really get a handle on the most complicated things. So the world is both simple and complicated. And it's simple at the level of the laws of nature, the unseen laws, and it's complicated at the laws of the happenings, the events and the outcomes that arise from those laws.
Okay, thank you very much.